Hello, this is Taneil Uttal here. I will be talking to you today about observing capabilities here in the Physical Sciences Laboratory. I'd like to take a moment to introduce my subject matter experts who helped me to develop this presentation. Those include Paul Johnson, Alan White, Alex Boranovich, Chris Farrell, and Heist DeVore. I would also like to mention the many people in the Physical Sciences Laboratory who have also contributed to this presentation. You'll note in this presentation, I really don't have any citations of papers. I don't have people's names listed who helped develop any of these instruments, observing capabilities or retrievals, or any of the things I'm going to be talking about. And the reason is this really is a whole laboratory effort to come up with all of the information that you're going to be seeing in this presentation. First, I'd like to talk for a minute about what does PSL measure. And our specialty areas are the surface energy budget, clouds and precipitation, and the boundary layer and tropospheric structure. And I put together a little graphic schematic here so you could have more of a sense of all those different things. And there's sort of some little preview slides here. You can see over there on the left that there's some little wind vanes going, and we've got some extreme water events. We have things going on over the ocean. There's the boundary layer, there's turbulence, there's a little chemistry symbol, and then we have things going on in the Arctic with all the different kinds of transfers of heat, energy, and momentum that we have between the atmosphere and the underlying surface, whether it is ice, snow, open ocean in the Arctic or in the tropics, whether we've got hydrometeorological processes going on over Western California or wind energy projects. I think of what we do is not making individual observations of individual variables, but taking observations of essential systems. And the 4 essential systems that we have a focus on in PSL are air-sea interactions, the Arctic system, the hydrometeorological system, and the planetary boundary layer and tropospheric structure. And those 4 different kinds of systems, we are investigating all of those and in terms of their relevance to the 3 PSL themes, which are water, extremes, and the marine system. And I have along the bottom here, you can see a few graphics that gives you some examples of some of these different structures that we look about that we will be discussing in more detail. We have what we think of sort of metaphorically as the PSL quiver of instruments. And I've divided these in this slide into 2 lists, into the remote and the in situ sensors. And I won't read through this list, but you just can sort of glance at it and you can see that we have a large array of assets at our disposal. And I would like to pause here and talk a little bit about the remote sensors, because PSL has a history of merging, and one of the laboratories that it merged with was the Environmental Technology Laboratory, which was formerly the Wave Propagation Laboratory. And those laboratories had a strong focus on developing new observing technologies. And many of the profilers and radars and lidars and interferometers that are used for environmental research now across the different agencies were actually developed originally by NOAA laboratories, and many of the personnel from those laboratories are now part of PSL. So we operate some of these things with great expertise and understanding of how they operate, what kind of data they collect, and how it can be used. So I think the important thing that we do with all these different instruments that we have in our quiver is that we are an expert at bundling suites of instruments into integrated systems. And I have 3 examples here. In the upper left, we have the atmospheric surface flux station. That is a system that was developed in partnership with the National Science Foundation. And that picture there shows a system that is sitting out on the Arctic ice pack. It sat there for an entire annual cycle, and it was designed to run semi-autonomously with only refueling once a month. And it has sort of a little diagrams there. You can see all the different things that it was supposed to measure that would characterize not just surface meteorology, but the surface energy budget. So the higher order measurements that you need to understand what's going on between the atmosphere and the Arctic ice pack. In the middle, lower, we have a mini flux system, and it is indeed mini, and it has been designed to be deployed on uncrewed aircraft systems and actual aircraft. And it is very expert at measuring small scale turbulence, and which is an extremely important variable that you need to know if you're going to understand cloud development and boundary layer development. And one thing that you'll hear a lot about in presentations during this review is the Atmospheric River Observatory, which is going to be very important for atmospheric river research. One of the important things that I'd like to emphasize about these 3 bundled or integrated systems is that each of these systems was designed and put together to answer very specific, hard questions that we need to answer. For instance, for the ASFS, we need to answer the question, what is the annual cycle of the sea ice surface energy budget? And one of the questions we need to answer with the mini flux system is what is the variability of turbulence for scales spanning centimeters to tens of kilometers? And for the Atmospheric River Observatory, there's a fundamental question, is will the atmospheric river event cause flooding conditions, and where will those occur? I have a sort of a short collection of the types of data that these 3 different systems can collect. And what you're seeing here over on the left with the ASFS is the catching. This is just one of the variables. I think this is surface temperature here, and we're catching the characteristics of exactly when the Arctic ice pack started melting. And not only that, but with all the ancillary measurements that we have with it, such as long wave, short wave radiation, and sort of a ground heat flux, I guess it's a snow heat flux, and snow depth, we can start measuring what are the actual physical processes that force the melt. In the center here, I have a little example data from mini flux, which is distribution of vertical velocity at cloud base for cloud capped and clear eddy, clear eddies. And you can see how the distributions change markedly depending on where you are in level in the cloud and whether it's cloudy or cloud free. And finally, for the Atmospheric River Observatory, we see that there's not only meteorology, but there are physics involved that inform real-time forecasting of precipitation events. Another thing we do that is a part of observation science is creating advances in measurement strategies. We had a year-long program called de-ice, which was the de-icing comparison experiment. This was part of something that my research group got involved with as part of the Baseline Surface Radiation Network. This is a global network for observing radiation and is trying to inform sort of what the net energy we have coming in and out of the entire global system. And that group has different working groups, and one of the specific working groups was the Cold Climate Issues Working Group, and they had identified the problem that these different kinds of broadband radiometers for measuring shortwave and longwave radiation in the Arctic were having operational problems with frosting and riming that was contaminating the data set. And so we organized this program with, I think, 14 or 15 different institutions and manufacturers of these broadband radiometers. And a lot of people had been playing around with different kinds of mitigation strategies with ventilation and heating. And we kind of did a bake-off, we call it, where we saw how all these different instruments performed under the same conditions in Barrow, Alaska. And you can see in that figure down in the lower right, you can see how the different radiometers were reacting to different kinds. Some of them actually would stay clear. You can see those little glass domes. That's the important part to stay clear, not just the housing. And not only that, but we were keeping track of what the power requirements were for different systems so that people could make choices about what was the best system given the environment and what the power options were going to be for the environment that they were going to be deploying in. Another thing that PSL specializes in is retrievals. And by the retrievals, I mean a science of modeling measurements to obtain higher order geophysical variables. If you go down to the lowest common denominator, actually most measurement devices, maybe all measurement devices, are actually measuring a voltage or a resistance. And to even get something simple like temperature and all the things, all the kind of variables that you take for granted, you have to apply calibrations and you have to apply sort of relationships and standardization curves and things to actually get to the geophysical variables that you want. And but retrievals goes an even step order higher than that, where you start taking measurements, often for more than one different instruments or instruments operating at different wavelengths, and you combine those together to get an even higher geophysical variable. And for instance, here I have on the left-hand side, you can use these vertically pointing dual wavelength radar measurements for ice hydrometeor shape. And so you can look at ratios of Ka and W band reflectivities and look at how those vary as a function of Ka band radar reflectivity. And you can see that you start getting groupings in different regions of that space that can actually help you to identify hydrometeor shape. Another example that I have here briefly is on the right-hand side is the use of angular and frequency dependencies and reflection coefficients to actually get soil moisture. So once we collect all this data, we of course get into the problem of data stewardship. And that is actually a very difficult problem. Data gets collected from measurement systems in different formats. They get calibrated in different ways. And right now, the entire research world is, and the services world is struggling with this problem of how to manage and standardize and share and distribute all these different kinds of data that collected and how they can be made into usable products. And we have spent a lot of time discussing things with data management groups, and I kind of have decided that there's like a whole number of things that data managers care a lot about, which I have in the circle in green over on the left, and then scientists kind of tend to care about sort of other things. And the reason is we have different objectives. Data managers care about this long-term stewardship frameworks. They're putting together the libraries and the card catalog systems. And scientists care about just getting their data as fast as they can into research and publications and conclusions. So we are working by taking, if you look in the center there, what is needed is observing teams, modeling teams, and operations teams to be working very, very carefully together so that we can bring together what the data management and the scientific research community care about. And our end goal is to promote an advanced level of data usability and interoperability to expedite both research and predictive services. PSL in the last 5 years has, I think, gotten much more sensitive to this issue. We have a number of data sets that we have collected, have been published in journals such as ESSD. We are moving forward briskly with getting data set DOI assignments. And we also work with these novel metadata method, and we have these systems called datagrams, which kind of track, I think of it as tracking observational data from voltage to the end archive, where it really talks about what is recorded by, for instance, your data logger, what the specifications, what the calibrations, what equations you have to apply, where that data ends up. And this is sort of a metadata method that is useful for operators and users and data managers alike. I've got one website link here, and so for our PSL data curatorship, this is the link that you would go to see where our different data sets, we sort of provide sort of a portal access to a lot of different kinds of data that we have, that we are collecting with our different observational systems. Now, I'd like to take a moment and talk about some observing highlights for the 4 different categories that I discussed, or rather the systems that I discussed that are a specialty for PSL. So first I'm going to talk about for air-sea interactions. PSL is the originator of a very famous core algorithm, which has characterized how the ocean and the atmosphere exchange heat and energy. It's a flux algorithm. And now the sequel to the core algorithm is the core G algorithm, where PSL and collaborators have pioneered direct observations of trace gas fluxes over the open ocean. And you can see over on the left there is the core G algorithm, which is based on, I think, over 30,000 hours of data collection. And down below in the little box, you can see a list of the different gases that have been modeled by this flux algorithm. So you can see what kind of open ocean measurements. And I will mention here that this has been done with a number of collaborators. I do not have all their institutional logos on here, but that is something that this partnership has been very fruitful with the Physical Sciences Division. Another observing highlight for the air-sea interactions is the PSL contributions to Hui buoy, and we have assisted with adding some of these flux and atmospheric measurements. And the really amazing thing is to get something as high in order as these kind of IR fluxes, solar fluxes, heat fluxes, getting those in near real time. So this is sort of an operational development, which should be very useful in informing things like process-oriented diagnostics, which I will discuss a little bit more towards the end of this presentation. For the Arctic system, I have this graphic here. One thing that we have spending a lot of time on is organizing and sort of facilitating coordination between the Arctic observatories that are operated by the 8 Arctic nations. And if you see that graphic over there on the left-hand side, you can see that all these different stations by the 8 Arctic countries are all operating observatories. And by observatories, I mean facilities that are collecting data about how things are changing, or excuse me, why things are changing and not just how things are changing. If you have a MET station that is collecting state parameters, you know that things are changing, but you don't know the reason why. If you start measuring things like surface fluxes and atmospheric constituents and cloud radiative properties, then you start understanding about why they are changing. And in that graphic, you can see I have in the middle of the Arctic Ocean is a rendition of a German research vessel, the Polar Stern, which was the base camp for the recent Mosaic campaign that you'll be hearing about in the campaign presentations. But what we've been doing in PSL is not just assisting with these observations, but the facilitation and coordination about how all these observations are going to be used together. We have been doing that primarily through a WMO project called the Yacht Site NIP. It's the Year of Polar Prediction Site Model Intercomparison Project. The purpose of that project is that a number of modelings from the leading world forecasting centers are creating what they call model time step data, especially at the location of these different observatories and over the Mosaic ice camp. And model time step data is very high frequency. It has a cadence of like 7 or 15 minutes, and they calculate a number of intermediary variables that usually are not saved, but in this case they are, so that they can look how the processes in the model are working. And they want to compare that to very high cadence observations. But when you think about these observations are coming from dozens of sensors from a dozen locations and operated by many, many different individuals and researchers and institutions, the question about how to put these model and observation data sets is a really sticky thing. And so we are endeavoring right now to put up with these to come up with these interoperable model and observation data sets that are going to facilitate the process-oriented research that we wish to do. Another observation highlight for the Arctic system is that we have the coupled Arctic forecast system model here in PSL, and you'll hear more about that in the forecasting presentations. And one of the unique things about this particular model is this particular sea ice forecasting model and the development of it is being based on observation-based physics and verification. And if you look over there on the right-hand side, you can see for a plus 12-hour and a plus 24-hour forecast, we have the CAFS model output minus the observations. This is for a single site. And in the red, the thing that's interesting about this, in the red, you have an atmospheric comparisons, and you have in the center there, you have a light blue surface measurement comparison, and then down below, you're looking down below into the ocean, so that you have both the ocean, the sea ice level, and the atmospheric level as they're developing this model. An observing highlight for wind resources, which I think of as being in the category of our studying of the planetary boundary layer and tropospheric structure, is looking to see what the impact will be as you add additional instrumentation on the skill of numerical weather prediction models, specifically for forecasting these wind ramp events, which are very important for the wind energy researches community, because they have this very uneven inputs as the winds come up and the winds come down. They have to figure out when to store things, when to shed energy, and how they're going to deal with this sort of chaotic and formally unpredictable resource. And so over there on the right, you can see that there was a very specific study done, and it looked for different forecast hours, what kind of skill improvement you got, depending on whether you used your remote sensors only, whether you used your in situ sensors, or you combined the two. Another observing highlight is the hydrometeorology, from the hydrometeorology group, is PSL has an award-winning vapor flux product. And one of the most important parts of this water vapor flux tool is that it combines model output with real-time and past observations, so forecasters can judge how well models are portraying weather events. And we have some output there on the right-hand side that I'm just showing you briefly about what you can get from the Atmospheric River Observatory portal, which again is something that I know that you're going to hear a lot more about from the hydrometeorology presentation. My last few slides here is I want to give you some kind of a sense about the fact that we actually go out into the field and we actually put ourselves out in that environment, and we do these measurements. We're not sitting behind our desk at time. We go out where the action is. And for this example about how some of our observations are supporting PSL extreme sciences or extreme science, and I'm showing you an example of the PSL wide swath radar altimeter, which goes out on the NOAA Hurricane Hunter and produces real-time mapping of the hurricane ocean wave fields. And that is a very important data set that we have been managing for many years. In terms of observations supporting the water resource management, we had this heavy precipitation event during the second 11 February 2017, which resulted in excessive runoff into Lake Oroville and leading to the Oroville Dam incident. And what I put over here on the left is just an indication. I asked the hydrometeorological groups in PSL, how many observations do we actually have in the physical sciences laboratory that are supported specifically by us? Because this is an extensive observing network. Part of it is actually PSLs, and part of it is the state of California. And there are other groups like UNAPCO that also operate instruments in coordination with us. And so you can see little tiny red numbers over there on the left, and those are the assets that actually belong to the physical sciences laboratory and that we operate and that we integrate into this great network system. Another example that I have here is, and I really like this one because I actually took this video myself, and what we're looking at here is icebreaker. This is a Russian icebreaker that's moving through the Russian ice camp, or through the ice pack, and it is bringing me back from an ice camp that I was at for 4.5 months this last winter as part of the Mosaic project. And with the reason that we are doing this, that will be very specific to the kind of research that we're doing here in PSL, is the Mosaic program was designed to measure all components of the system, not just the physical environment, not just the atmosphere, but the atmosphere, the snow, the ice. And then you can see the extensive ecosystem that exists underneath. And I put little circles in red around the little fish there because we think about this as supporting the blue economy in cold places. And right now there's an international agreement to prevent unregulated high seas fisheries in the Central Arctic Ocean. And NOAA needs to start, and the nation need to start figuring out how to provide the environmental intelligence to support these kinds of policy decisions about how these kind of international agreements will be implemented. Looking forward, I just have a couple of slides. One is on process-oriented diagnostics. That's kind of it seems like a very buzzy word these days, but the idea is we are going to develop models and assess model performance by looking at these processes. And in this particular case here, we are doing comparisons between a UFS benchmark run, both for July and on the left and for December on the right. And we're looking at relationships between the stability temperature and the long wave radiation. And you can see for the winter time or the summertime and the wintertime months, you get very, very different distributions of those two variables, which you can see in the top and the right panels, and that you can actually start making conclusions that the model is having less cloud cover in winter than the observations and too much in summer. And so you can start trying to assess what is happening in the model so that they're not getting these critical variables correctly. Another looking forward sort of topic is NOAA is thinking more and more about developing a Bering Sea observing system. That's an area where is the location of a lot of the fishing stocks that are collected by the United States. And so they need a lot of information there. And it's a prime location for looking at atmosphere, ocean, and sea ice processes that impact both the marine ecosystems and weather forecasting, not only for Alaska and the lower 48. And this red boundary that I'm showing here is actually the official US Arctic Research and Policy Act definition of what we consider to be the Arctic. You never know exactly where we're going to draw those boundaries. Is it going to be the Arctic Circle or something different? But this is, the Bering Sea is well within the official definition of Arctic for the United States. So in summary, I have 5 sort of concluding comments here. And the first takeaway I want you to have is that science questions drive the development of the observing systems that we operate in PSL. And the observations we take need to answer the why, not just the how, if we're going to develop any kind of physics-based understanding of what's going on with these different systems. And right now, there's a lot of work being done on developing these coupled models, but the understanding of these complex coupled processes between different parts of the system requires measurements of the individual components of the coupled system. And that is really a specialty for PSL. And finally, we have the opportunity with these boots in the field kind of operations to do observations of subgrid scale processes that are necessary for proper representations in models that you can't do with gridded data sets from, for instance, satellites. And finally, the importance of these process level observations is they really challenge the models to get the right answers for the right reasons. I'll be looking forward to discussing this more with everybody, with my subject matter experts during our panel discussion. Thank you very much.